Welcome to this quantum security and defense presentation. Thank you for being a valued member of our community. Jakub Mielczarek, associate professor at the Jagiellonian University, is a theoretical physicist working at the Institute of Theoretical Physics. He heads the interdisciplinary quantum cosmos lab team, exploring new research areas at the intersection of theoretical physics, cryptology, and advanced technologies. He is also the coordinator of an academic hackerspace, Garage Complexity, cultivating an environment that encourages students and innovators to turn scientific and technical ideas into reality. He teaches cryptography, quantum gravity, and discrete mathematics.
Cryptanalysis, and based on some of the research that we conducted, I want to share with you some of reflections because as you know, there is a lot of noise around quantum cryptanalysis, around specifically in media. We are hearing different kind of information, not necessarily verified one. And my little goal for this talk is to introduce a little bit of I would say order to what we know about cryptanalysis and what we can forecast from the perspective of present. So I'm not going to go very into math, into the details behind, but I have to introduce just a little bit of ideas, just that you know what we are talking about. Okay, so the leading idea that I want to start with is related to superposition attacks, and the superposition attacks are they relied on a feature of a quantum world, which is quantum parallelism. And let me I think simply explain what we mean by that. So if you have a classical computer, let's say that you have old 32-bit computer with a 30-bit register, at a given moment of time, your register takes a given sequence of zeros and ones, okay, which encode your information. So the very difference between classical computers and quantum computers is that you can prepare your a quantum register, I mean the register of a quantum computer, in a superposition of a different sequences of zeros and ones. Specifically, if you have those 32 bits, you can prepare the so-called quantum superpositions of all possible sequences of this kinds, which are about 4 billion, okay? And this is the sum representing a superposition, quantum superposition of all those possibilities. And thanks to that, just with a single query to your quantum register, you can act on all the different states of the classical quantum register. So this is something very, very different from what you have in classical computing. And the quantum parallelism, which is kind of a way of manifestation of quantum superposition, is exploited by superposition attacks. So just to give you a basic example related to superposition attacks, let's focus, for instance, on some classical cipher. Let's say that you have a plain text M and you have a ciphertext C, and you have some encryption function with a given key. Let's say this is 256-bit key, like in AES cipher. So then, just with a single, I would say, set of operations on the quantum register, you can generate all possible Ks. So in classical word, this is something crazy, okay? It's 2 to the power of 256 is a huge number, but here in principle, just 256 qubits allow you to do that. I mean, the logical one. And then you can use a certain type of quantum operation on your quantum register, which is called quantum oracle. And by the action of this quantum oracle, you can produce a state in which, I would say, in the first part of the register, you have all possible case, and in the second part of the register, you have accompanying values of your encryption, so the ciphertext corresponding to a given plaintext. So you have the so-called a quantum database. So you have just in the superposition of states encoded information about all keys, which a huge number, and the corresponding ciphers corresponding to a given message or the plaintext. So now the task is to explore that quantum database, and there's a couple of options for that. The basic one for an unordered quantum database is the seminal Grover's algorithm, which introduces certain improvement for finding elements in the quantum database. However, this is not a very significant improvement. This is just a square root type of improvement. But anyway, this might be useful for a certain application, specifically for chosen plaintext attacks, if the number of bits is sufficiently small. There is another algorithm, and actually that's historically the first quantum algorithm which proved exponential speed up, okay, with respect to the known classical counterparts. And the Simon's algorithm, because we are talking about the Simon's algorithm, actually is finding a collision. A collision is when you have some function and you find two different arguments that this function gives a certain value. And here, specifically, this collision is when you XOR the two values, this gives you a certain a bit sequence S, okay? And it turns out that this problem can be mapped into various cryptanalytic techniques, specifically in the context of Ivan Mansur, Lubirakov, or Lai-Messi symmetric ciphers. And actually, based on the Simon's algorithm, Shor, who was a reviewer of Simon's paper, introduced the seminal Shor algorithm, which is about actually generalizing the Simon's idea to the arguments of the functions, which are integers. And this way, you map the problem of finding the collision to finding a problem of the period of a given function. And this problem of finding a period of a given function can be thereafter mapped to the factorization or analysis of the cyclic groups in elliptic curve cryptography. So this is a theory. This is a basic theory, I would say, with respect to the quantum algorithm, which are used for quantum cryptanalytic techniques. There are more, but I want to focus just on those three here, which are, I would say that the basic ones. But of course, the basic question is how close or how far are we from the practical use of quantum cryptanalysis with actual quantum computers? So to address this question, I want to refer to two different, I would say, measures of the quantum computing resources. And of course, the basic one that you are all familiar with are qubits, which are the basic, I would say, elements based on which we build the quantum register, the basic degrees of freedom. But typically, let me emphasize, we are referring to the physical qubits, the number of qubits in the hardware. However, the big problem is that those hardware are extremely noisy for the moment. And we need to apply different kind of techniques like quantum error mitigation techniques, or eventually quantum error correction codes, which are just at the beginning of introduction to the real hardware. But at the end, when we refer to quantum computing, I would say techniques, specifically in cryptography, we will need to know how many logical qubits, those logical qubits that we use in quantum algorithms, can we obtain. So this will be addressed in a moment, but let me show the current trends for physical qubits. So we have like a 100 noisy, or maybe even few hundreds currently, still very noisy quantum beats, the physical qubits. And what we observed that there is a roughly tenfold increase over 5 years now. Okay, so and of course, you know, in information technologies, going back to the discovery of the transistor and construction of the first microchips, we observe different geometrical trends, like a seminal Moore's law. And this Moore's law, of course, is observed not only at the level of number of transistors in the microchips, but it's observed in the very different circumstances. And there is a reason actually to believe, to assume that the similar trends might also be present in the area of quantum computing technologies. However, they are still at the very early, I would say, stages, and we have to treat all of those considerations with the reserve. So we discuss qubits, but qubits are not enough to really quantify available quantum resources. So if we want to do predictions with respect to quantum cryptanalysis, we cannot rely just poorly on number of qubits, because they are not enough. And another, I would say, the parameter which is extremely crucial is the depth of the quantum circuit that we can execute on a given quantum hardware. And this is currently, I would say, that the leading limitation of a quantum computing. And this is related to the so-called quantum decoherence. Okay, so that in time your quantum system is coupled more and more, I mean, with your environment, and the quantum properties of your state are vanishing. So therefore, we have this limitation on time, and eventually the number of the layers in your quantum circuit that you can execute on a given hardware. And this is something what we can also quantify. And there are different measures introduced recently for that purpose. And specifically, one which has been broadly investigated is the so-called quantum volume. And basically, I don't want to go into the technical details of that, but basically the quantum volume tells you what's the biggest square type quantum circuit that you can execute on your given hardware. So the number of qubits and the number of layers is equal here, okay? And if you look on quantum computing technologies, there is a progress with quantum volume. and primarily the progress is limited with the quantum decoherence and the depth. Okay, so you can go to the bigger number of qubits, but still you are limited, in this temporal direction. And the biggest progress in the recent years has been made in case of ion-trapped based quantum processors, and this is because you isolate in the magnetic or electromagnetic traps your ions, and the impact of environment is well under control. And specifically in the quantinuum class of quantum processors, the current quantum value is about 1 million, okay? And how to understand this 1 million? Actually, this is huge number, so it looks like, oh God, we have something which is really big, okay? But at the end, actually, this number is telling us what is the size of the, more or less, the space of the superposition, the so-called Hilbert space. But from the viewpoint of qubits, what we have to do is to take a logarithm of that value. And if you take a logarithm of that value, it takes you 20. Okay, so this 20, roughly 20, tells us that with this quantum computer, we can execute a general quantum circuit with 20 logical qubits and the 20 layers of the gates. Okay, so such a square type of quantum circuits, and this is all what we can do with respect to the general quantum circuit. Of course, currently there are some processors with which we can do more with respect to a certain type of quantum circuits, and design such that they fit to the architecture. But when we address, a kind of general problem, we want to understand how much we can do with a general type of a quantum circuit. So currently we observe more or less like a tenfold annual increase in quantum volume. But of course, when you take a look at the logarithm of that, this increase is lower. And also here we have I would say, the first stage of some further evolution. We don't know how this will go on, but there is a chance or kind of expectation that it might follow a geometric increase over the next years. So of course the future is very uncertain. It's very difficult how those two trends are, I would say, with respect to the number of physical qubits and the quantum volume will continue in the next years, okay? But it's for the purpose of this discussion, it's good to have some reference, I would say, value. So to build kind of imagination of the possible futures, and to build that imagination about the possible future, let me do the following. Let's assume that the physical qubits will follow the same tenfold per 5 years trend over the next years, and the quantum volume will follow basically a similar, this is like a tenfold, I just assume here a little bit better, 100-fold per years. So what could be the future if we follow those geometric paths? Okay, so if you take a look at the time perspective of 25 years from now, with the physical qubits, okay, we can have around 10 millions of physical qubits, and for the quantum volume 10 to the 56. It looks huge, okay? However, as I said before, actually the physical interpretation with respect to the quantum resources is related with the logarithm of base 2 of that number. And if you take the logarithm of that number, it gives you 185. So it tells you that if the current trend is preserved, then in 25 years from now, we will be able to simulate a general quantum circuit with approximately 200 logical qubits and 200 layers of them. And in my opinion, this is quite reasonable. I think we will get there in 25 years, okay? And if you want to go further, and of course, this is very uncertain, many things can happen meantime, but if you would keep that trend for the next 50 years, that would increase up to, let's say, up to 400. Okay, so I mean, you will be able to simulate or execute a general quantum circuit of the size 400 per 400. So I want to now refer those numbers, those imaginations with respect to the possible future, with our understanding of the security of the symmetric ciphers. So let me first emphasize that for symmetric ciphers, we are generally lacking of any proofs of quantum security. Okay, we don't have. There is actually just a couple of cases, like a Lubirach of Feistel cipher with the 4 runs for which we can prove quantum security. But in general, we don't have mathematical proofs for that. We believe that they are secure based on the size of the key, the space of the key. But still, there can be some sophisticated attacks in the future that we currently have no idea about. But there is actually, I think, a useful concept that I introduced with respect to analysis of the threats of symmetric ciphers specifically. So there is we can formulate a strong sufficient condition for security, namely for any quantum attacks that you can imagine with respect to the symmetric ciphers. A first step is always to map your classical encryption scheme into a quantum processor. This is like a first step. Any attack, any quantum attack requires that step. So the strong condition for security is as I said, okay, if you can implement your algorithm in your quantum register, you can go further. Okay, so let's relate that to AS 256. I would say the current standard for symmetric encryption. And currently, the most optimal known implementation requires around 6,000 logical qubits and a depth of around 1,000 layers of gates. Okay. So based on that, of course, this is it's not a square type of quantum circuit. It's a rectangle. But based on those number, you can find a kind of estimate for required quantum volume. So this is at least 1,000, and the sufficient number is of the order of 600, such that you have 600 qubits and 6,000 layers of your quantum circuit. So this number is somewhere within that range, okay? So if you compare that, okay, with what we observed before, we are still away from that value, okay? I will return to that. So let me come to asymmetric ciphers like elliptic curve cryptography, RSA, and other currently used asymmetric ciphers, which are based on the different versions of the discrete logarithm problem. And we can implement the short algorithm here. And there have been a lot of discussion on that in literature. In particular, there's an important paper from 2019 showing that we will require like a 10 million of physical qubits and about 8 hours of the coherence time. So you say, okay, the 10 million physical qubits are reachable within the perspective of 25 years. However, not with respect to the coherence time, which gives us eventually a huge number for a quantum volume. And we can actually do the calculations for that. We know the scaling. There is still an improvement over years with respect to the implementation of the Shor algorithm. But we know basically how the number of qubits and the depth of the circuit scales with the number of bits in your encryption scheme. And for RSA 2048, this translates into the following requirements. So at least 6,000 value of the logarithm of the quantum volume is needed to implement that circuit. Okay, perhaps more. Okay, I typically take a geometric average of Bode's number to give you something of the order we could expect. So is there anything to fear based on that? Okay, so if we follow those linear extrapolations, basically we will remain safe for the next 25 years in the sense that this will be very difficult to break those ciphers like AS256 RSA or elliptic curve cryptography with the size of a key like 256 bits. If we apply those naive extrapolations, like a first order approximation to what can happen in future, of course, still many things can happen. But if you take this as a kind of your first approximation, we can be safe within 50 years time frame. And let me emphasize that the main difficulty is related to the depth of the quantum circuits. As for the current standards, the depths of the circuits are huge. Okay, like I mean, with superconducting quantum computers, our coherence times are the level of microseconds currently, and for RSA 2048, you need like 10 hours. Okay, and there is a huge gap between the 10 hours and the 100 microseconds. And there was not much progress with respect to the coherence time for superconducting quantum computers over the next 10 years, actually. However, okay, let me stress that we cannot rule out scientific and technological breakthroughs which might occur within the next 20, 30 years. From now, there is for sure, there will be for sure a significant impact of AI for our scientific and technological progress, and very different things can happen over the years, affecting those trends. However, this is still very, very uncertain. So my approach is basically to closely monitor advancement in quantum technologies to detect signs of such development. So if we want to really better describe what's the risk and somehow quantify it probabilistically, we have to understand in details what the current limitations and prospects with respect to quantum computing technologies. And in particular, with respect to the sensitive type of information with a long lifespan, I mean, the preventive measures should be implemented if they are already available. And I have a question: how much time left, if any, left? Do you still have like a couple of minutes?
Yes, of course. Yeah.
Okay. Thanks a lot. So let me just briefly say about two of them. I would say the two possible countermeasures which are currently under very advanced development. And one is, of course, the post-quantum cryptography, which is designed such that the classical ciphers are made resistant to all those attacks that I discussed. And specifically, they base on the problems which are either NP-complete or NP-hard, and they are not within the so-called bounded quantum polynomial type class of complexity, to which all those problems which are attacked with a Simon or Shor algorithm belong to. And there's a plenty of options with respect to the mathematics and given problems that can be adopted for that purpose. And importantly, since like 3 months now, we have first 3 standards for PQC announced by NIST. We have FIPS 203, which is a lattice-based problem based on the crystal Kyber algorithm, which replaced the standard key exchange like a Diffie-Hellman, specifically based on elliptic curves with a so-called key encapsulation mechanism. So this is already as a standard, and currently this is under implementation. And another standard, which is actually another asymmetric type of encryption scheme, which replaced the digital signatures based on either RSA or ECC. And there is one more actually standard, which is based on hash functions. Actually, I didn't refer to hash functions before because hash functions are believed to be secure with respect to the quantum cryptanalysis. This is still a belief. Okay, we don't know all the possible vectors of attacks yet, I would say. They are under investigation currently, but anyway, they are used for the constructions of the post-quantum standards. And we have QKD, which is very nice theoretically because this allows us to introduce the so-called IPS level of security. This is the highest level of security we can imagine. This is based on the theory of information, so we can always narrow the number of bits that can leak from our transmission. And you can prove that for the quantum protocols. This is really well developed. Also at the interface with the classical cryptography. However, the problem is with implementations. Okay, there are still backdoors attacks and other type of attacks which utilize some imperfections in implementations. Okay, this is something currently under investigation. They are costly, however, also, and basically designed also for very specialized applications due to that dedicated infrastructure. So it's not like just replacing hardware, but they are already available solutions. There's a picture of the Polish solution made at the Warsaw Military Academy in Warsaw. One more thing, just to finish, is that of course the question is where we want to apply all those encryption schemes and all those countermeasures, and this is specifically the communication network. And if you take a look at the basic OSI layers of the networks, where you have a physical data network and transport and application layers, those countermeasures can be already introduced at the different levels of the security. Specifically, like a MACSEC a protocol can be made post-quantum. Network layer IPsec can be either made just post-quantum, but there are also currently implementations which involve QKD, quantum key distribution. At the transport layer, the TLS is currently very actively migrated to PQC. There are also links to quantum key distribution. And of course, at the application layers like SSH, there are currently already emerging PQC versions of those protocols. So this is really ongoing migration happening right now, and those standards by needs only trigger that migration. So just to summarize, quantum computing is definitely, they pose a potential threat to some of the cryptographic primitives currently in use, both symmetric and asymmetric. However, when we systematically analyze the resources, the quantum computing resources which are needed to implement the quantum cryptanalytic techniques for the purpose of attacking those primitives, we find that those resources, in comparison to what we have now and what we could expect in about 25 years from now, are way behind. Okay, so we are still not yet there, to thinking really seriously about the opportunity to perform quantum cryptanalytic attacks on the current cryptographic primitives. And to really make reliable security assessments concerning quantum cryptanalysis, and this is also something what we dig a lot into. We are actually also building a quantum computer in Warsaw, which is kind of also the platform not only for quantum experience, but also to understand all the limitations that we currently have with quantum hardware. This allows us to make a better prognosis forecast for the future. And definitely for long life information, specifically with the lifespan about 50 years, the quantum cryptanalysis should be definitely considered in risk assessment. Okay, this is a risk factor. We know that this might be a case, okay, that something can happen, but the likelihood is still very low. And importantly, if you face this kind of problem and your risk assessment tells you, okay, I should already made some steps to prevent those potential threats, we have tools to counter-react. We have PQC standards. We have PQC-based protocols, like a TLS currently, so for the communication in internet, and we have quantum key distribution. And as I also outlined, there is a path currently for migration of the different layers of the TCP/IP or OSINT models, depending which one you prefer, to pass from the current, I would say, classical cryptographic primitives to something what in future might prevent you from any quantum attacks that we can currently imagine. Okay, so that's all basically all I want to say. Just a list of figures that were used in the talk. Thanks. So I'm open for questions, of course.
Thank you very much, Jakub. Do we have any questions, ladies and gentlemen? If you could message us in the... So I've got a couple of questions, Jakub. So what, in terms of, you said that we're monitoring the progress of the innovation in terms of the capability to crack levels of encryption. What specific technologies do you see as being the sort of threats to crack or to expedite the cracking of the encryption?
So I can say that, I mean, with respect to the superconducting quantum computers, that will be very difficult to reach a level that will enable for a realistic quantum cryptanalysis. So I would exclude, based on the current understanding, that the superconducting technologies. And I would focus on those which are the most promising with respect to the coherence time. So where you can isolate best your quantum degrees of freedom from your environment. And these are specifically the ion trap based approaches. There are of course different challenges, but they are promising. And certainly photonic approaches. Okay, I mean, with photons, basically you can keep your coherence for a very long time. And if I would have to just select those technologies which are the most relevant with respect to the potential of quantum cryptanalysis in far future, that would be those. Okay, the ion traps are natural atoms based, and the photonic ones. If that was your question.
It was indeed my question. Thank you for that. I was talking to myself there for a second. Another question from Bill. Have you looked at the recent digital quantum computing that Google has referenced lately through Dr. Ed G? They broke the RSA 2048 modules on the test site. He was able to do it with the original format of RSA and do it instantly.
How many bits?
I mean,
Sorry?
that's a question.
He was breaking off the RSA test site, which they've changed the modulus since their key was compromised in Mexico a number of years ago. So they changed the algorithm a bit, but he was actually breaking the keys on the test site, including 2048, and in basically real time, using a digital quantum compute platform that he has created. So it's, you know, the thought, and, you know, I've been following many different approaches by, you know, combining, you know, or you know, in an older kind of version of basically daisy chaining the compute of different quantum computers. AT&T was doing it a couple of years ago, where they were combining different sites to run the algorithms with great success. You know, it wasn't real time by any means, but you know, it was in the several month category of shorter key lengths. So, you know, this 25 years, I'm you know, maybe I was on another call, so I missed the beginning. I just think that's almost misleading, to be honest, because I think that we are much closer to having the math abilities to break it in a timely manner. You know, right now they say steal now, decrypt later. You know, it's a 5 to 10 year period. You know, watching with, you know, Google started looking at this gentleman's math. He's out of the West Coast in North America. His last name's Girk, Dr. Ed Girk. He is different. He's really smart, but he is different. To be polite. I actually saw the results from the test moduluses, and I'm you know, I'm not a big fan of going out and breaking RSA in real time, because that's a bad thing. But misleading, I think 20 to 25 year time frame, you know, you will bankrupt many companies, but I also don't believe it's a valid statement.
I think that was based on the current capabilities, Bill. I think you probably came in.
Yeah.
Just
Okay. And you know, I'm sorry, I was on a call and I was about a half hour late. So, but so that is just my thought on it. And you know, I think that I don't know if you guys have been following the TikTok type stuff with going on in the US and elsewhere with regards to data access and such. That's where we have to really look at the QKD type approach for our authentication. That way, it lock it down, and unless you have, you know, something to unlock it, you can't see it.
Thanks, Bill. We've got one more question, and people have asked if you could just share your slide deck on the LinkedIn. One more question, then we'll move to Tony. And that is, I've been working on several projects implementing tools to protect against quantum attacks. What can be the most critical infrastructures to protect?
Of course, we start with like with respect to the networks. You know, this is really costly. I mean, so all this hardware, specifically with respect to QK, this is a costly stuff. So we specifically think about like backbone networks, and this is something under implementations currently. Also in Poland, actually, we have our quantum network for communication between the data centers is ongoing currently. We have a bunch of links. So and of course all the government type and military applications are included, of course. So specifically those areas, of course, where you have a long span information type, and you have enough money to pay for a given security countermeasures.